Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 36, dosage calculations based on body surface area. Today's objectives are to describe the difference between body weight-based dosing from BSA-based dosing, learn how to calculate BSA from height and weight using equations and using nomograms, learn how to calculate doses using BSA, and understand when you can apply BSA-based dosage calculations. Now, people usually try to use BSA-based dosing strategies when there is difficulty normalizing the drug dose per body weight, and these are special population groups such as neonate infants, obese, and elderly patients. Disease states and conditions where the drug disposition may not be normal, for example, cancer, drugs with narrow therapeutic index such as chemotherapeutics, and of course a combination of all of the above. Now, in an attempt to better correlate drug dosage with organ functionality, clinical scientists have to look for other indices, and one of the most famous and still in use is the body surface area. Now, in the past, it was thought that dosage approaches based on BSA are more accurate than dosage calculations based on body weight, mainly because BSA estimations are based on two parameters, weight and height. Now, of course, we now know that that's not true. Now, some of the accounts on this matter even mention that BSA approaches account for organ size and function, which is, of course, is not true. And obviously, I do not share this opinion. In order to confidently use BSA equations to calculate doses, you have to be able to see the connection between drug disposition, organ size, and body size. And of course, this is because we are talking about body surface areas, right? Now, our attempt for the next 5 or 10 minutes is to try to derive these body surface area equations. And that would allow us to also see the connection between the body surface area, the weight, and the height. So we're going to start by simulating our body as a cylindrical object. Now, the surface area of a cylinder can be estimated from the surface area of the sides. So this is the surface area of the side, as you see here, plus the surface area of each of the base, okay? So we know that the surface area of the sides is 2 pi r h, and the surface area of the base is pi r square, and we have two bases, so that would be 2 pi r square. So equation 14.1 expresses the surface area of a cylinder. Okay, so here now I'm using two cylinders of the same height, okay, 1.72 meters, but of different diameter, just to see the effect of the diameter of the radius or the diameter on the surface area. So here, surface area A, which has a bigger radius, is of course bigger, 2.12 meters square, whereas the surface area B with the smaller radius, okay, you see that it's 0.159, it's 1.88 meters square. Now, at this point, let me go back for a minute. We do not see the weight factor here, right? We can see the height. So when the height is the same, but the radius is different, that of course causes differences in the surface areas. How can we determine the weight of the mass of a cylinder? All we have to do is to calculate the volume of the cylinder, and for our purposes use a density equal to the density of the water, since we are mostly composed of biological fluids, right? Okay, so now the volume of a cylindrical object is given mathematically as pi r squared times h, and of course we are familiar, mass is equal to the density times v, right? And mass now is the weight, so the weight is equal to the density times pi times r squared times h. Okay, so what I did is I substituted v for the weight over density. Okay, so what I did over there, so from here, let me just write it here. V is equal to the weight over density, and now I have weight over density is equal to pi r square times height, and therefore the weight is equal to the density times pi times r square times h. Okay, and this is what you see in equation 14.3. So now the weight, using this equation 14.3, the weight is correlated with the height. Okay. We also know that if we factor density in there, we know that the cylinder with a bigger radius that corresponds to a larger surface area will be heavier, although the height is the same. Okay. Now, over on this slide here, what I'm attempting to do is to estimate the percent contribution of surface area of the two bases. And what you can see here in the case of the surface area of the A cylinder, the two bases, their contribution to the surface area is only 9.4%. And when I did that with the cylinder B, which had the smaller radius, the percent surface area of the two bases was 8.5%. So since it is less than 10%, for the time being, we can just neglect those two. So eliminate them from our equation. And therefore now, our equation becomes a surface area equals to 2 pi RH. Okay? Because now this one, since it is only 10%, we're just going to eliminate it from the equation. Okay, so now all we have to do in order to derive our equations is to factor in our equations in the body surface area, the weight and the height at the same time. Okay, because as you can see here in this equation, we have the height but not the weight yet. But we have derived the weight on equation 14.3. So we're going to combine these two equations and derive an equation that hopefully resembles the well-published BSA equations. Okay, so let us do that. So here we have equation 14.3, and assuming this equal to 1, this will become, I'm just going to write it over here, W is equal to pi r square times h, and then I solve for r. So r will be the square root, so let me just write it here. So r square will be equal to the weight over pi over h, and therefore r will be the square root of the weight over pi over h. Okay, and I'm going to substitute this on equation 14.4, and when I carry out the algebra, I end up with this equation here. So the surface area is equal to 3.545 h to the 0.5, that's the square root, times weight to the 0.5. So now, this is amazing, right? We have derived a surface area that is expressed in terms of the height and the weight. And that's equation 4.5. Let us compare that equation that we have derived, obviously by a cylindrical object, with the published equation. So this is the Dubois and Dubois formula. Consider resemblance. 0.20247 times h to the 0.725 times weight 0.425. Look at the Boyd's formula. Okay, the Fujimoto's formula, the Heiko's formula, and of course the Mosteller's formula. The Mosteller's formula in reality is 1 over 3,600 times height to 0.5 times weight to 0.5. So it is very similar to what we have derived there. Obviously our parameter is much higher, but our parameter just came out of a geometrical object, okay? It didn't come out of studies with clinical patients. So now you know how the weight and height can be used to calculate body surface area. So this is what we have. Okay, so now the next question we need to address, body surface areas or body weight, which one is more accurate? So we have clearly seen, I hope you are convinced, that body surface area approaches, it just comes out of mathematics. So unlike pharmacokinetic methods, they don't take into account metabolic or other organ functionality differences in individual subjects. Differences in body surface areas are reflected into weight differences given the same density or composition of the body. We have proven that, right? When you have used the density and derived the weight there. On the other hand, different body surface areas may not lead to significant differences with respect to the weight if the dimensional differences are counterbalanced by differences in the body composition or density. So these are all possibilities. So then the question is that neither method, BSA or body weight, can be accurate in special populations or special conditions or disease states. Okay, so body surface area has no distinct advantage over methods based on body weight. In some occasions, body weight could be better actually than body surface area. So none of these methods can actually predict scaling up or scaling down. Those are just determined for normal individuals, for special populations or individuals with certain disease states or conditions, because neither approach uses functional parameters involved in pharmacokinetics. So this is the truth. All right. So when can you calculate dosages using body weight? So first, when it is clearly stated that you can do so in the package insert of the specific drug. So only when studies are done. This is what we're saying there. And of course, number two is when the patient is free of diseases and conditions that can affect unpredictably the pharmacokinetics or pharmacodynamics of the PK/PD of the drug. When can you calculate dosages using BSA, which this is more of a mystery? And again, when it is clearly stated that you can do so in the package insert of the specific drug. All right, if the drug is new, then you can do so when your patient has the same characteristic, age, gender, etc., as the patient group used to generate the BSA formula. So what you need to do first, when we go back to this table, let me just go back. All these formulas that you see are generated out of specific populations. For example, Boyd's formula is for pediatric patients. So you have to study the population group that is studied over there and see if your patient is similar to that group, then perhaps you can use the Boyd's formula. Of course, with caution, but you can go ahead and use it if you're a physician. And of course, when the patient is free of diseases or conditions untested in clinical trials that can affect the PK/PD of the drug. So essentially, what we are saying there, BSA carries no advantage to body weight, and you can go ahead and use BSA when it is stated to do so in the package insert of the specific drug. So this is the truth, okay? Now, let us demonstrate how to use BSA formulas for dosage adjustment. So let's assume that you can dose a drug using BSA. It is stated, it is written in the package insert. How can we do that? So the first step is to calculate the BSA of the subject from the height and weight using one of the formulas listed in the table, as I just showed it, or using the nomograms. And we can demonstrate both methods. Now, it is important to know that every BSA formula is represented with a different nomogram, because of course these nomograms are generated from the different equations. So every different equation has a different nomogram. So be very, very careful here. Use the correct nomogram. Now, BSA values read from a nomogram should be the same as those calculated from the corresponding formulas using the scientific calculators, because as I just mentioned, the nomograms were generated from the formulas. Okay, so this is a nomogram of for adults using the Dubois and Dubois formula. Okay, and perhaps we can use it later to demonstrate how to use it. Yeah, maybe here. Maybe we can use it here. Yes, that's good. So here we have a daily maintenance dose of a narcotic analgesic for a normal individual is 5 milligrams, assuming that the BSA for a normal individual is 1.72 square meter. And this is a value that you have to memorize for, let's say, NAPLEX exam or licensure exam for pharmacists. Calculate the drug dose for a 180-pound, 6'3" subject, and must be an adult, of course. It cannot be a pediatric patient, right? That height. Using the nomogram, and here I specify which nomogram anyway, and using the Dubois formula. So we need the two different ways. So first, let us use the nomogram. So this individual is 180 pounds, and that's his weight, right? And his height is 6 feet 3 inches. So that would be 75 inches, right? 72 plus 3. Okay, so what I'm going to do, I'm going to go back to nomogram here, and I'm going to mark here on the weight column, I'm going to mark the pounds. It's 180. So here we are, okay? So that's 180. And on the height is 75 inches. So this is 75 inches. And now I'm just going to use my ruler, and hopefully I can draw a line carefully. And the value on the middle axis is going to be the body surface area, okay? So let me just draw this, and here we are. So it's about 210. Okay, so that's my body surface area here, and it's labeled body surface area. Okay, so using the nomogram, the body surface area is 210. Okay, as I just showed it. Now, using the Dubois formula, the BSA is 0.20247, 1.905 to the this is the meters, okay, that maybe I have calculated here. This is the meter. This is 190.5 centimeters. So 75 inches times 2.54 centimeter per inches is 190.5 centimeters, which is 1.905 meters. Because, going back to the table again, here it says height in meters and weighting in kilograms, okay? So I'm coming back to the formula. So this is the meters, the height, and this is the kilograms. And I get the same answer. Now that I have the BSA as 2.10 meters, 5 milligrams is the dose for a normal individual, for which is 1.72 square meters. For a 2.10 meters, how much? So X is equal to 6.10 milligrams. So this is how you calculate the dose of an individual. It must always based on the dose of a normal weight of a normal BSA individual. Okay, so this is normal BSA. Normal BSA. So it's always by comparison. Okay. So again, first we calculate BSA, and then we use dimensional analysis to determine the dose based on comparison with the dose of a normal individual. If the dose of the normal individual is not known, you cannot calculate the dose based on BSA. Simple as that. Okay, so what are the disadvantages of the BSA approaches in dosage calculations? Well, first, and this is very important actually, BSA is not as perceptible a parameter as the weight. Because we don't use BSA in our everyday life, and it makes it difficult to judge whether an estimated BSA value makes sense for a particular individual or not. For example, we would question the weight of an infant reported as 20 kilograms. That's too much, right? But we wouldn't probably question a BSA of 0.65 meters square. Like this BSA here is not easy to know that, hey, this is too big or too small, okay? So that's one disadvantage. Caution also is recommended to choose the correct formula presented in the appropriate format. Among the plethora of formulas, some of them actually dedicated to special populations. This is what I just mentioned before. You need to make sure that you choose the correct formula, the correct units for the correct population. My advice here is that read the package insert and use the formula that is written there. Also, books and manuscripts sometimes may have the formulas copied down incorrectly. I've actually seen it, all right? And use of nomograms is easier than using the formulas, but they carry the risk of having graphical errors. That also has happened in the past. So these are the disadvantages of BSA approaches. So again, my advice is use the package insert to dose your patient. The advantages of BSA approaches in dosage calculations is because they use two adjustable parameters, they appear to be more flexible. However, this is not accurate, but it is an advantage because these BSA approaches have been tested in clinical trials on a group of patients, in a large group of patients, and their formulas have been statistically adjusted to be accurate for these population groups. And this is what I mentioned in the second paragraph. Always remember that you cannot use a BSA formula generated out of one group of patients with certain characteristics to those patients that do not share those characteristics. If they do, then you may try to dose your patient using body surface area, okay? Now, in example 14.3, I'm attempting to demonstrate the validity of body surface area for neonates versus infants, and explain in pharmacokinetic terms why these formulas could be quite accurate, and when could they be used though, that it should be drug specific. That's what I'm referring to. So here we have two formulas that they were recommended for neonates, and neonates is 1 month old, less than 1 month old, and infants, which is 1 to 24 months old, so basically up to 2 years, right? So here is the formula for neonates. BSA is 0.0224265, height in centimeters, weight in kilograms, okay? And the formula for infants, the BSA is 0.0071. So this is a much smaller number than this coefficient, right? You can see that. So I'm asking, is there anything wrong with these formulas? And again, the answer is, how would you know, right? I mean, this is the first time you've seen these formulas. And how would you justify a bigger BSA for neonates? So first we have to prove that anyway. Okay, so of course there is something wrong with these formulas because it was copied down incorrectly from a book. So this formula, the correct formula is 0.024265. Notice that the formula that was copied incorrectly in the book, it had one additional 2 here. And that made some difference. Okay, so perhaps not a fatal difference, but it's not the same, right? Okay, so this is exactly what I mentioned before. It's so easy to make a mistake because these numbers are such, with so many decimals there. Okay, so when I plotted, so that's one problem. The formula is copied incorrectly. All right, so when I plotted these formulas, and here I have BSA versus height, and here I have BSA versus weight. Notice that in neonates, so that's the blue dashed line, the BSA is higher. So therefore the dose will be higher. And the same with the weight. The BSA, again, Haycott's neonates, that's the correct formula. This is the red dashed line. The BSA is higher, and therefore neonates would be taking a larger dose as compared to infants. And the question here is, why would a neonate, which is less than a month old, would take a larger dose than an infant, which could be like a 2 years old individual, much larger, right? So that's exactly all these points that we've been discussing. So why would neonates receive a larger dose than infants? So in this case, it could be explained from their physiology. So we know from physiology that the total body water in neonates is 75 to 80% of the total body weight, as opposed to about 70% in infants. So this is actually reflected in the volume of distribution. So this would be reflected in the VD, because we also know that these differences are most related to extracellular fluid. So neonates contain more extracellular fluid, or could be translated into higher VD, with caution though, okay, than in infants, which could be like 2 years old. So this could be true for specific drugs that have a relatively small volume of distribution. They are distributed mostly into the central circulation and extracellular fluid and interstitial fluid. Okay? So if the drug clearance is not affected by the difference in the activity of liver and kidney, neonates will require a higher dose to achieve the same therapeutic levels than infants, because they have a higher percentage of extracellular fluid. Okay, and that is reflected in the volume of distribution. But the catch here is that assuming that your drugs are mainly distributed into the extracellular fluid. So if the drug is hydrophobic, these formulas most probably would not be correct, would be very inaccurate and perhaps dangerous. Okay? So this is what I'm referring here. So for lipophilic drugs with large VD that are primarily eliminated by metabolism, a higher neonatal dose could be very inaccurate, because the liver may not be able to handle large doses. All right? So this is exactly what I was talking about. Be careful when you use BSA. It is perfectly safe when it is stated to do so in the package insert, but that's all. Okay, and here I have some practice exercises. 14.10 is a theory, and it's asking you to pick the correct statement, whereas 14.4 is a calculation that is quite common, and frequently you see this kind of calculations in the NAPLEX exams. And here you have the answers. So at this point, I would like to thank you for your attention. Until next time.